I think we can all agree the cube resistive circuit is one of the complex circuits out there. So let's see how we can find the equivalent resistance in different cases of a cube resistive circuit using symmetry. I highly recommend you to check this video in our channel, which will prep you for what is to come. In short, we are going to solve the cube resistive circuit using the concept of equipotential points, that is the 2 points which are at same potential.
So let's start off with the simplest case first, finding the equivalent resistance across any edge of the cube. Here we have a cube resistive network with all the resistors having a value of 1 kilo ohm. To better understand what is happening in the circuit, let's connect a voltage source across the edge of any voltage, doesn't matter. Here I have taken it as 5 volt. Now if we consider this point to be having a voltage of 5 volt, then this point here will be at 0 volt. That is, the 5 volt by the source gets dropped across the entire resistive network. Now we need to identify the equipotential points. Let a total current of I is flowing, which splits as I1, I2 and I3. By symmetry, we can say that currents I1 and I2 should be the same. You can visualize this by seeing the resistive path ahead of the current I1 looks exactly same as for I2. So if the resistive paths are equal, currents will split equally. That makes I1 is equal to I2, and let's take this current as I0. If the current in these two branches are same, the voltage drop they give across these resistors also will be the same, since V is equal to I0 into R.
Just a reminder here, this is only if the resistors are same. If I get a question on cube resistive circuit with different resistors, I'll probably find something better to do rather than solving it.
Anyways, now if we have the same voltage drop across the resistors, then the remaining voltage appearing at these 2 points will be phi minus the drop, that is phi minus I0 R, which is the same for these 2 points.
Congratulations, we found out our first set of equipotential points.
Now applying the same approach towards the merging ends, we can say that if current I splits as I1, I2 and I3 at the start, then the current in these paths should be I1, I2, I3, which then combines back to give I. Again, this is due to symmetry.
Am I saying symmetry too many times?
We know I1 and I2 are equal, again symmetry. Therefore, the drop across these resistors are same, which makes these two another set of equipotential points. Now the thing about equipotential points is that they are at same potentials. Hence, it wouldn't hurt if we just merge them. They are literally the same points. Okay, merging the equipotential points gets us an equivalent circuit like this, which is solvable pretty easily. We see these 5 set of resistors where each 1K is connected in parallel with another 1K, which gives us an equivalent of half kilo ohm. Replacing these resistors gets us a much more simplified circuit. Oh, here we have half kilo ohm, 1 kilo ohm and half kilo ohm in series, which is an equivalent of 2 kilo ohm.
Now 2K and half K are in parallel, that gives a 2 by 5K,
which is again in series with half kilo ohm and half kilo ohm, which is 7 by 5 kilo ohm. Now finally 7 by 5 kilo ohm is parallel with 1 kilo ohm, and we get 7 by 12 kilo ohm as the answer. So the equivalent resistance across any edge will be 7 by 12 kilo ohm.
Next, we will find the equivalent resistance across phase diagonal. Approaching the question the same way as previous, we connect some 5 volt across the phase diagonals. This point is at 5 volt and this point at 0 volt. Current I splits as I1, I2, I3. The resistance circuit ahead of I1 current branch is similar to ahead of I3 current branch. We can take I1 is equal to I3 is equal to I0. Therefore, I1 and I3 are equal. This means drop across these two resistors are same. Therefore, the voltage at these 2 points is same as phi minus I0 R, making them equipotential points. Similarly, if I1 splits as I1 dash and I1 double dash at this node and I3 splits as I3 dash and I3 double dash, we see I1 dash and I3 dash should be equal because of symmetry. Thus, the drop across these two resistors are same and the remaining voltage appearing at these 2 points will be the same. Thus, we have the next set of equipotential points. Now we merge the equipotential points. These parallel 1 Ks can be converted as half K. Replacing with half Ks, we get a simplified circuit like this. Here 1 Ks and half Ks are in series, become 3.5 K. Now we have a Wheatstone bridge setup. Taking the ratio of resistors on the same side, we get half K by 3 by 2 K, which is same for both sides. Thus, the bridge is balanced. Therefore, no current flows through this half K. We can remove this resistor, further simplifying the circuit. Now, half K in series, we get 1 K. Similarly, 3 by 2K, 3 by 2K in series, we get 3K. This 1K and 3K will be in parallel, thus we get 3 by 4K. Therefore, the equivalent resistance across phase diagonal will be 3 by 4K. So, the last one, let's find out the equivalent resistance across the body diagonal. As usual, taking a 5 volt connection across the body diagonal, this point is at 5 volt and this at 0 volt. I current splitting as I1, I2, I3, we see that for all three currents I1, I2, I3, the resistive path ahead is exactly the same, making I1 is equal to I2 is equal to I3 is equal to I0. Therefore, drops will be same for these resistors and thus making those 3 points as equipotential points. Similarly, at the other end where the currents I1, I2, I3 combine as I, since all these currents are equal, drops in these resistors are equal, making these points as equipotential. Now merging the equipotential points, we get the equivalent circuit like this. These set of 3 resistors are in parallel, which reduces to equivalent of 1 by 3K. Similarly, here these 6 resistors are in parallel, which becomes 1 by 6K. Now 1 by 3K, 1 by 6K and 1 by 3K are in series, gives us a total of 5 by 6K. Hence, the equivalent resistance across body diagonal is 5 by 6K. There is much more simpler way of calculating the equivalent resistance across the body diagonal, and it's possible only due to the tremendous amount of symmetry that is present in the body diagonal case. We cannot do the same approach across the edge or across the phase diagonal. They don't have that much of symmetry. If you're interested, do check these shorts explaining the same. As always, I will see you in the next video where I don't say symmetry anymore.